Hi, this is Mr. Manley. Let's go ahead and take a look at some properties of radicals here. The properties that we keep coming back to are that the square root of a times b is equal to the square root of a times the square root of b. That's one thing. Another thing that we keep coming back to is that the square root of a over b is equal to the square root of a over the square root of b. So you see how we can split these radicals. What we cannot do, we do not say that the square root of a plus b is equal to the square root of a plus the square root of b. That is not a property of radicals. That is not true. For instance, if we looked at the square root of 6 plus 3, we know that 6 plus 3 is 9, and the square root of 9 is 3. But if I tried to split the radical and said the square root of 6 plus the square root of 3, well, that does not equal 3. Square root of 6 plus the square root of 3 does not equal 3. And then finally, just going back to the principle, the fundamental definition of radical, which is that if I've got an nth power, and of course this n, maybe not of course, maybe you don't know, this is called the index. So if you've got your index, then it matches, or if it matches the power on the radicand, which is what this is, the part that is under the radical, then we can simplify it like so. So these are the properties of radicals that we're using here and the definition that we're operating off of. So when I look at the square root of 50 here, to start with, I'm going to factor that to 25 times 2, and then I can use that multiplication split property and say that this, and then I know that the square root of 25 is 5. Okay, here I've got the square root of 12 over the square root of 15. All right, something interesting is going to happen here. It's not a property of radicals, actually. So this is a property of radicals. I can do that, right? And this is a property of radicals. I can do that, right? And look what we have there. See, this is not a property of radicals. That's common factor, canceling a common factor. Rad 3 over rad 3. That simplifies things for us. The square root of 4, we know is 2. And then I've got rad 5. And then we have this idea that we want to rationalize the denominator. That's part of the definition typically, at least up through pre-calculus, that simplify means you should have no radicals in the denominator. And how do we address that? I'm going to multiply by some form of 1. All right? Rad 5 over rad 5 is simply multiplying by 1. So I'm using the identity property here. And why did I use rad 5? Because in the denominator, that's getting me a non-radical result. Well, something that I said at the outset was we know that the nth root of a to the n is equal to a. Something else that I could say is the square root of a times the square root of a is equal to a. So this is something else about radicals that we know. If I had a different index, say I had a cube root of a, then I would need 3 of them. So I'd go cube root of a times cube root of a times cube root of a. That's equal to a. Okay? Just reviewing some radicals here. So what do I have in this denominator now? Let's see here. I've got 2 rad 5 over 5. And that's what I want. This one up here in the middle then is simply a case, we already did this, right? Rationalize the denominator. In this case, rad 5 over rad 5. 10 rad 5 over 5. And then this 5 cancels with a 5 there. 2. And I get 2 rad 5. Okay, this is good. Looking below here, we'll look at at the different index, right? So what needs to happen here? The cube root, and I see that I can split up 16 into 8 times 2. What about the 12? Four and 3. Really not going to be able to do anything with that, right? If I have 4 times 3, neither of those is a perfect cube. So I'm stuck with that cube root of 12. And then the cube root of 8 is 2, right? Because 2 times 2 times 2 is 8. So I've got 3 2's there. And the index says if I've got 3 of a factor, then I can simplify the radical expression. Okay, so you might see something here, maybe not. But what I would have to do at this point, I'd have to do something. And I can't just leave it the way it is. So what if I said 2 times 12 is 24? And I've got cube root of 24. Oh, well then I can factor the 24 now to 8 times 3. Now somebody might have recognized up here that I had a 4. 4 times 3 is 12, and a 2. 4 times 2 is 8. So you could have seen the 8 back there. One way or another, you get to it. And now I've got here 2, and then the cube root of 8 is 2. So that's 2 times 2 is 4. And cube root of 3. Very good. And looks like, okay, a couple more here. Oh, and I got one over here. All right, so here we go. This is looking a little interesting. I'll tell you what I'm thinking about when I look at this. I think about, are there going to be any cube factors in this? So I think, is there a 2 cubed? No, 60 is not divisible by 8. Is there a 3 cubed? 60 is not divisible by 27. Is there a 4 cubed? 60 is not divisible by 64. So I've got nothing here. Let's look in the numerator. What about the 140? Is that 140? I'll go about it a different way. Instead of thinking of the divisibility like I did with 60, I'm going to look at the factorization. So what do I have there? 4, and then that's 3, 5, 7, 5. Okay. Now what someone might do at this point, they might recognize, okay, we're stuck here, but I've got to rationalize the denominator. I can't simplify everything, but I've got to rationalize the denominator. Someone could go like this. This is not what I'm going to do. But look at this. Someone could go like this. See that? 60 times 60 times 60. And then that would rationalize the denominator. Oh, but I'm sure going to get a little bit of a mess up here, huh? Perfectly reasonable approach, but I think I've got something better. Remember back here, we had that little trick, right? Whoops. This little trick here. Yeah? Rad 3 over rad 3. Let's look for some of those. So I'm going to factor this. And what did I have? I had a cube root of 4. I want a cube root. Cube root of 4. Cube root of 7. Cube root of 5. Was that it? Yeah. 20 times 7 is 140. And in the denominator, I think that's divisible by 4, isn't it? 60 divided by 2 is 30. 30 divided by 2 is 15. So that's 60 divided by 4 is 15. And what do I do with 15? Cube root of 3, cube root of 5. Hey, look, 4's cancel, the 5's cancel. Well, this is much more manageable. Cube root of 7, cube root of 3. Now, do you know how to rationalize this denominator? Do you remember how to do that? I need to multiply. I know I need to match the radical, so I know I need to match the cube root. And then I need a number here so that when I multiply these two, it's going to be a perfect cube. One way of thinking about that number is not to think about the number, but just to go, well, if I've got 1 3, I just want to get 2 more. So 3 times 3 would be 2 more, and that would be 9. Okay, so numerator is cube root of 63. Can't simplify that anymore. And in the denominator, I've got the cube root of 27, which is 3. And there we go. It's always interesting that there's always different ways to think about it. Like, I mean, I could think about this as the cube root of 3 times 3 times 3 and get to my 3 that way. I could think about it as the cube root of 27. And, well, I know the cube root of 27 is 3. And then sometimes there are other ways to think about it as well. I guess the cube root of 3 cubed. I know that's 3. And they're all the same. It's just a different form of the same thing. Okay, what do we have here? Simplify the square root of 18 times x to the 9th. Again, there's a lot of ways to think about this. One thing I'm going to do is this. I'm going to split up the 18 like that, so I can just see. Someone might just skip up to 3 rad 2. I think I like to see it for myself, and certainly when I'm looking at students' work, I like to see their thinking. All right, how should we think about the square root of x to the 9th? Some people might be able to just jump right to it. I'm gonna show you a way to think about it that some people might like, some people might find unnecessary. I'm going to split it up into x to the 8th times x. And then what do we have here? I've got the square root of 9 which is 3. So we've checked that off. I've got the square root of 8, which is x to the 4th. And then I've got, so that took care of that. And then I've just got these other two here, the 2 and the x. So there, simplified. One more. Okay, as I'm looking at this, I'm definitely thinking, is there anything I can simplify with this fraction? Is there anything there? And the answer is no. I'm also looking at the cube root. I think it's nice to go ahead and split it here to see what's going on. So cube root of 8. Oh, look at that. Cube root of a cubed. Bingo. And then here, cube root of 25. And okay, I have the b to the 5th. How about that? Are you thinking about that? B to the 5th, that's the cube root of b cubed times the cube root of b squared. You see how I split that up? B to the 5th is b cubed times b squared. And the cube root of b cubed is b. So we've got some things to work with here. Cube root of 8 is 2. Cube root of a cubed is a. Cube root of b cubed is b. And then I've got this 25b squared left over. So in my mind, I immediately think, well, to rationalize this, I'm going to need a cube root of something. And what's it going to be? Well, I've got 2 5s, so I need another. And I've got 2 b's, so I need another. And I'm allowed to do that as long as I do it over itself. So I'm actually just multiplying by 1. And when I multiply by 1, nothing changes. I've got $1 million times 1. I've still got $1 million. Okay, so let's just bring this home here. 2a cube root of 5b. And follow me in the denominator here. If I've got b, let's start with the numerically first, okay? So I've got the 25 and the 5. So I've got the cube root of 3 5s, which is 5. And then I've got the b and the cube root of b, that one and that one. So the cube root of b cubed is b times b. B times b gives me b squared. One last check. Can I cancel anything here? No. And that is it. If you had trouble with radicals in algebra or algebra 2, hopefully this will help you. And most of all, go ahead